All right, welcome back. Beautiful weather. It's actually going to get up to like 45 in the next couple of days, so it's another one of these weird little storms. So what I want to talk about is the homework before we do too much of anything else. And somebody has turned the microphone way up again. So what I want to look at is a couple of examples of homework. Some of you did really great. Some people did something, instead of creating a flow chart, what you actually did was took a scenario and just detailed how that scenario would play out. It didn't have decisions, it didn't have... So you were telling a story about one event that might have happened versus looking at it in terms of creating that logic behind it. So a couple of examples here that I thought were really good. This one's a little big, I'll have to make it a little smaller to see. Go ahead and do that right now. Chunk. So, in this particular case, this isn't one I ask you to work, but it kind of shows what one might look like. So, one of the things I noticed, a lot of people didn't use the right symbols. They just put whatever symbols they wanted to do. And the reality is, we use these same techniques, these same ideas in flowcharting, not just in a programming class. You're going to use those in business courses when you want to understand a process. So it's not a horrible thing to do to learn to do these. And there are some additional symbols. Some of them have, but the basic symbols that we have here are kind of the easiest way. So in this particular case, it says we're trying to find a word in a dictionary. So we know we have a start and we have a stop. We open the dictionary. That's a task we do. It doesn't make any decisions. And then we ask, is the word on the page? So if the word is not on the page, so in other words, if that word does appear, so there, when we have that double negative, we got to be careful how we do that. No, then we stop. So if we are on the right page, we don't have to do anything else. If not, so the word is not on the page, and that equates to true, then we have a selection. Is the word greater than the last word on the page? So in other words, do we need to flip forward or backwards? And that's what this is asking. So yes, turn page forward, and then we go back up. And here's where a lot of people also had an issue. They brought those loops and they went way up to the top. That loop has to start and end in the same spot. In other words, it begins and ends right up there where that little connector is, and we have to return back to it. So that's where that priming the pump input. This one doesn't have a priming because it's a little different example, but in most cases, you're going to have the same action or the same input here as you do directly above the loop, and you have to have that in there. So that one is how to find a word in a dictionary. And in fact, if you looked at the pseudocode then, and I think it's easier to do the flowchart because the flowchart gives it that graphic piece. So here it says open the dictionary while we don't have the word, if the word is greater than. So anytime we have a selection, that's an if then. So in this case we say if the word is greater, turn the page, else, so the opposite condition. So if true, else false, we turn the page backwards. So that if then, have you guys done those in Excel before? Because we can actually write the same logic in Excel. If you want to make those kinds of decisions in Excel, we can do those also. And we'll show you how to do that before we get done with this course. So there's our flow chart. So here's one, and there's a lot of variations on there, and I know a lot of people did this one, so I threw out a sample of this. So this is a customer coming into a store. So in this case, we simplified it a little bit here at the top. So we have add item, price to total. In other words, they've scanned an item. Does the customer have more items or into file? Some people used. Yes, add item. So we just continually create that loop right there. And that gets us all of our products in there. In this case, we say does the customer have a coupon? We added in another piece. And so if yes, we subtract that discount. And then we have a display total due for the customer. Is the customer paying cash? In this say, accept the cash. Here we even added a little loop for, does the customer need change? Yes, give change. Now, could you make those much more elaborate? Those are still fairly high level. Yeah, you could make it more elaborate, but in terms of understanding the process, this is kind of the flow and how that works. And we look at those in business and say, yeah, we need to look at this. How does this process work? And sometimes we rearrange how our customer service reps or how our systems work based on looking at these tools. Because we say, you know what? Most of our customers hand us a credit card. So can we make a process that's more streamlined for that? So maybe it's as simple as having card-only lines. And we've probably seen those when you went shopping where it said, credit card only, no cash accepted. Because we know it takes a longer time for people to process cash. So that's an example of, if this one will fit on the screen. Let's see if it will. If I can make it fit. Might have to make it a little smaller here still. A little smaller so we can see it. All right. So this is a diagram for the game of war. And when we started some of the card games and some of the other things, when people started writing them, they get a little more elaborate. And so this is war. War is pretty simple. We realize how we play war. It's 2 cards, you match them up. So this is a good example of that. Let me make it a little bigger so I can see it. All right, so the first question we have in here is, we're gonna start this and say, yep, we're gonna play war. All right, so we ask a friend to play. If that friend says yes, then we deal out my hand and your hand. So we deal all the cards. If we look at this, that question, that no, I'm not sure why it's not showing up in there. Go back in one more. Oh, maybe it's just broken the thing here. So no then dumps us all the way down to the return piece. So we're just looking at both players. We turn over cards. My card equal to your card? If it is, because most of you when you did war forgot the whole piece about actually having the war when I looked through there. So if my card is equal to your card, yes, we put the cards on the table, and then we start over again. Now, we don't have the part about where you deal out 6 extra cards and all that silly stuff. But this is an example, what are they doing outside, of the game of war. And if we look at the pseudocode for it, you'll start to see how important this indenting becomes. Because if we didn't indent, this would be a spaghetti piece of code. We wouldn't have any clue what it is. And those indents let us know at what levels pieces are going to happen. And so some of you, when you did the pseudocode, didn't indent. You just have this block of text. Well, the indentations are how most programming languages and how we, when we do this, understand those things are all in there. So if we didn't indent this, I wouldn't know that this if statement over here is inside of this one. So I will post those up so you guys can look at them and take a look at those for examples. Most of you did really, really well. There were a few that, like I said, instead of describing an action with possibilities, in other words, that you play the game of war, you detailed me how a game of war went. You said, well, my friend and I both had cards, and he had a king and I had a queen, and you detailed how one scenario went. And we use those as an example of when we're doing something called a desk audit, but in this case, what you're trying to do is create some code so you could create a game that plays, because we don't know what's going to happen in this particular game until we work our way through it. So indents, 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 indents. And that was probably quite frankly, the biggest thing I saw when people did this pseudocode. They wrote it all and then flattened it to the left. And so there's no way to tell where you're at in that particular code. So I will post that up. So last week, we gave you the secrets to the entire class. There's only 3 pieces. There's only 3 pieces. There's a selection, a decision. Remember that computer, though, that computer can only do zeros and ones. Only can do zeros and ones. And then we started out with a loop. And the loops we described to start with are what we call do-while or while loops. So they continue to execute while a condition is true. So sometimes that leads to us writing things a little weird. So the while not, so in other words, we're saying while this condition equates logically to true, it may be a false condition. So you'll see in there, we always want that loop to run on the yes condition. In other words, that we have made a logical true statement. So here's our sequence. So just a list of things happening in a particular row. And then we have our decisions. We also call this an if then else. So we have 2 conditions and we feed down through. And then the while loop. And it's got to re-enter here at the top. We almost always want to come through where this procedure where we're doing this loop while it's true, while this condition equates to true. So it does make it sometimes awkward when you write those statements in there. Everything we do, we can just kind of put those together. And I just stacked those up with my artistic ability and said, well, we can put those 3 pieces together, and that creates a flow chart. We don't have to have all 3 in a flow chart. So, but we have to have at least one of those structures to create our flow chart. And then we can put them together in other ways. So here we have another example of, in this case, we're looking at the game of Monopoly. Start, throw the dice. Move token, the space is equal to the sum of the dice. Did the token land on go to jail? Well, if so, we went to jail. Did the token land on chance or community chest? Well, if so, we follow those directions. And so we can write out how we do operations in almost any type of game. One of the problems we have, though, is we start getting bogged down in those details. And so a lot of times, what we do is we know how certain things operate. And so we can start creating modules or little pieces that we can go ahead and insert the entire module. So in this case, we wrote a module up here. And we wrote that module called housekeeping. And that housekeeping, all it does is set a number equal to 10. Now, it could do a lot of other things. But in this case, it says, we're going to set it equal to 10. And so I run that little housekeeping. I don't have to go through the entire set. I can just plug it in. And notice I can plug it in anywhere in this code if I want to. And I can start making modules. And that's one of the powerful things we can do with any of these programming languages, is we can start making these modules. Now, I've declared them out here, so they've got a start and a beginning. But instead of saying start, our nomenclature is to say, all right, we put the name of that module out there. So that's a housekeeping module. And instead of an end, notice what it has. It's got a return for it. And so we say, okay, so we start, we go through that, and then we return back. And that ability to add those modules makes your life a lot easier, especially if you think about a game like a game of war, that card game. That's a lot of details in there in those, flip 2 cards down. We could make a module for some of those. That way we go out and get it, we use it, and then we come return right back to it. So in this case, this one's also got one for something called detail loop. So inside a detail loop, instead of putting directions and all those pieces in there, we have a call to that module. So we say detail loop, and we're going to call that function or module as we're going to call it. And we come up here and we say, all right, so we're going to call detail. Detail loop outputs the number that we put in earlier. And then it says the number equals the number minus 1. So in other words, every time that runs, it takes that number and it decreases it by 1. And then it returns it right back where it started. So we don't have to put all of those pieces in there. We just know that that's contained inside of that loop. And that can make your program a lot easier. And so then we have a third module here that says finish up. And it says output into program. So it doesn't do a lot. But think about if we put other instructions in there, it would make our life a lot easier to deal with. Find my mouse here again. Come back, mouse. So this week we work on a lot about decisions. So we've already got some ideas about decisions. We put them in there and we said, well, we know that the computer can only do yes and no, but there's some other things it can do. And so you're going to introduce yourselves to this term called Boolean expressions. So in other words, we're going to have some way we can compare things. And these are nothing more than you guys have done before. You all know what ands are, right? Can you add 2 numbers together? Okay. Can you decide if one number is bigger than another? Okay. And so we're going to start combining these together and start thinking about how we evaluate that logic behind them. Because remember, that computer is pretty dumb. The computer is really, really dumb. All it can do is decide zeros and ones. That's all it can do. So we have a couple of different ways we can write those, and you've already seen them and already thought about it. Now we're just going to put it out a little more formally. So if I have a selection, so I'm asking a question, I can put in, there could be items that I need to do in both sides. So both no and in yes. So the no and the yes. So maybe I have a question of, do I go to school today? And if yes, I put on clothes, take a shower, and I go to school. If no, I stay in my pajamas and turn on Netflix. So there's 2 alternatives that we have in here. And both of them have some kind of action associated with them. But a lot of times what we really end up with are single-ended actions. So do I go to school today? Yes, get dressed. Otherwise, I'm not even going to do anything. I'm not even going to crawl out of bed. So we can write those comparisons or those selections with either dual actions or a single action. So that second action is that else piece. When I write if something is true, I do one action, else I do another one. So if then else tells me that I am having a dual alternative. I have 2 things. I'm making a choice between 2 activities. If then says we only worry about the one side of our equation. So it really just has to do with how we write those out. So in this particular case, we have a dual alternative in here. And so now we've got a little more complicated project. We're going to write several different pieces out. We have different types of variables. We have some input then on top of that. So we've declared the variables. We've now got an input. And we ask a question. Are hours worked greater than hours in the week? So the question for this one is, we're trying to determine if you get overtime or not. So what do we set overtime at right now? Where do you get overtime if you're working for somebody? So 40 hours is generally considered overtime. So why didn't I just write 40 hours in there? So why didn't I just say hours worked greater than 40 instead of having a hours in week up here as a variable? Why would I do that? Well, I could compare. So you're thinking it couldn't compare it if I had a number and a variable. Okay, no. The reality is we want to almost always use variables versus hard-coded values. And part of the reason we do that, what if I needed to change this? So what if a new federal law came out and said, you know what? We're going to change overtime to anything over 38 hours. And I had hard-coded that in there. I would have to search through this program and find every place that it used 38 hours. What if I missed one? Somebody doesn't get paid enough, they get very grumpy. So we almost always use variables, even when it's a number we don't think is going to change, but what if it does? And so in this case, if that hours in a week that we had to pay overtime on changed, maybe we did it on our own. Our company said, you know what, we're going to be very progressive. We're going to pay overtime on anything over 30 hours a week. I change one declaration statement, and everything in my program then functions correctly. The same way with overtime rate. Could we change and pay 2 times the hourly rate? Yeah. And it would take a single change in that line. So we almost always write, for maximum flexibility, we almost always write everything as variables. Plus, even just looking at that, if this just said hours and work greater than 40, that 40 doesn't really tell us much. Whereas if we use very descriptive variable names, it tells us what that number is in there. Because if we didn't do that, we might have all kinds of numbers floating in our code. We wouldn't know which ones to change or what they do. And so this gives us a really quick, easy way to do that. So, in this case, then we say hours worked greater than hours in week. So if it's no, then pay equals hours worked times your pay rate. If it's yes, so in other words, if you have overtime, your pay rate equals hours in week. So pay rate times hours in week, plus you have to have that overtime piece. So in this case, they said hours worked minus hours in week times overtime rate times rate. And so sometimes when you construct those, you need to work that out in your head. Is this the way I want to do it? Is that the only way to write that? No. There are lots of different ways we could write that and structure that. But one of the things we want to do then is take test models. And so you could say, hey, I've got somebody that's making $10 an hour. They worked 50 hours. And work through this logic. Does that actually make sense? So in either case, both of them come down to a single statement that says output, name, and pay. And so when I say output, does that mean it goes to a printer or a screen, or can it go into another program? So that output really says, I'm done with it in this program, I'm sending it somewhere else. We're not really saying that we're printing it to the screen, we're showing it on the screen, we're printing it to a printer. It may be that this is a module inside of a payroll system, and then it sends it back into the database or other places. So we're making those decisions then. So Boolean really just means we're making a decision, and generally we call them true and falses, or zeros and ones. So true is 1, 0 is false normally. So everything we do in our computer program, that's all we can do. So because our computer can only do zeros or ones, those true falses are kind of our natural form of evaluation. Now, we have some trickier pieces we're going to get to here, because unfortunately the world isn't always just a true-false equation. But we have some other ones we want to do. So these should be really familiar, nothing that you guys didn't do in 4th grade, right? You guys know what the equal sign is, right? So the equal sign, when we do it as a operator to compare, so it's a little tricky in here because now we're going to use the equal sign for two different things. One, we call it an assignment operator, and that's where we put a variable in and we shove a value into it. So we can use it as an assignment operator, but we also can use it in comparisons. So a lot of times you'll see what we actually do for this when we want to compare. And in a lot of computer languages, what they do is it's actually two equal signs side by side. So logically, that way we can separate those. But we say, all right, so if an evaluation or expression is true, that means those are equal. So if I had 4 is equal to 4, that evaluates to true. If I have a greater than operator, so that says the thing on the left is greater than the thing on the right. Less than means the opposite. Greater than or equal to, or less than or equal to, very similar except for that little quirk of including that number itself. But here's one you may not have used as frequently. Not equal to. So it's not greater than, not less than, it's not in some way equal to. So we combine the less than and greater than symbol. All right, so you may also see really commonly in a lot of computer languages, or a lot of the way people will write stuff, you'll see the exclamation mark and the equal sign. And that will also indicate not equal to. So whatever our expression is, we're now seeing does that translate then to a true or false. So in this particular case, this is that idea of that not equal to. So here, we could have written it a lot of different ways. But in this particular case, we're giving a discount in some case. So we give discounts based on the customer code. That customer code, we want to see, in this particular case, a customer code of 1 would give us a value, and anything else gives us another value. So if it's not equal to 1, they get a 0.25 discount. So anything else other than 1, they get that 0.25. So that's one way to write it. Could we have written that a different way? Could we have said if customer code is equal to 1, and we just would have had to flip those discounts around? The yes and no would be there, and we'd have to flip discounts from side to side. So we can write that same question in a couple of different ways. And that's what makes it a little... So there's the same thing, but now we're saying customer code is equal to 1. So notice what we did if I flip back and forth between them. The yes and the no are on the same side, but where did the discount go? Notice I flipped those discounts around. That is the same thing. And it depends on how you like to write and structure things, which way you might want to do that. The same thing. The end result, the customers get the same discount, here's where it starts getting a little trickier. So it's pretty easy. We have one question. Life is pretty easy. One question we can figure out. But when we start combining them, it starts getting a little more complicated. So, ands, typically we look at them, they're called a nested decision. But we can also think of it as a compound decision. We're asking multiple questions. So, let's think about, is anybody in here in a sport? Yeah, you guys are going to go, okay. So, to be eligible for a sport. So, if I want to play, we'll pick on football. So, if I want to play football or basketball or anything at Peru State, but let's pick on football. If I want to play football, I have a couple of things I have to do. Do I have to be eligible by the NCAA or the NAIA? Yeah. So there's some criteria there. Do I have to not have graduated? Because I can't keep playing football for 7 or 8 years, right? So there's some limits on how many years I can be here. Do I have to be academically eligible? So all of those conditions are and. So I have to be eligible by the NAIA. I have to be eligible by the school. So both of those conditions have to be true. So when I say we want an and decision, it looks somewhat like this. So in this particular case, we're looking at a sales guy, saleswoman, salesperson. And if I look at this, there's a couple of criteria that we need to look at. So salesmen work on bonuses and commissions, right? So in this particular case, they have to sell a certain number of items. So items sold greater than items minimum. And so that items sold is how many items they've went out and sold. Items minimum, then we look up there, it says it's 3. So if they've only sold 2 items, they are not eligible for a bonus. And in fact, it will, if you say nope, and it'll pop out that they do not get a bonus. On the other hand, if yes, they did sell greater than 3 items, it leads to a second condition. Is the value sold greater than or equal to the value of minimum? So in other words, they have to sell 3 items, and the value of those items has to be greater than $1,000. If that's the case, so if they sold more than 3 items, so maybe they sold 4 items, it moves into this question. The value sold greater than value minimum, they sold $1,500. Yes, and then it says bonus given equals bonus. So in other words, it adds in a bonus at that statement. So both of those conditions have to be true. And you think, well, that seems kind of a convoluted way to write that. But the ands, we know that both conditions have to be true. So the reality is, logically, either way we write that. So if I did the item sold first or the value first, either way it will actually work, and people will only get the bonus if both conditions are true. And if I look at the pseudocode, it's really nothing more than a nested if-then statement. So if condition A is true, then condition B is true. When we write it out, though, it starts to get a little more convoluted. One thing we have to worry about, though, is efficiency. So if I go back here, either way I write that, it would work. So if I flip those two conditions around, either way is going to work. On the other hand, in a lot of cases, I want to decide which one of those decisions I need to make first. And I do that for the fact of efficiency. Even though our computers are really, really fast, but in some cases, by choosing one or the other first, we can make a difference in how well our program runs. So, this particular model, we said, all right, so we're going to look at it flipping those decisions around. So, but we put some values in there. So in this case, we start out, we know there's 1,000 salesmen total. And if I look up here, see if I can get my cursor over there, it says, all right, this particular way says 100 salespeople are eliminated. So of those salesmen, 900 of them sold more items than were required to get the bonus. I then move down into the second part of my and statement, and so 900 people are entering this. And in this case, it happens to be an equal split. 450 people sold more than the value in minimum, and 450 people didn't. So we drop off another 450 people, and 450 people get a bonus. Okay. So either way we run this, the same number of people are going to get a bonus, 450 people. So I flip to the alternative model. So I flip this direction. And again, the same number of people here enter this sleeve. 1,000 salespeople. But we ask the question of, did you sell more than the value minimum? In this case, we take 500 people out first. They didn't sell a high enough value in total. So what happens then, only 500 people go through this decision process. So we dropped off the 500 who didn't sell enough product in terms of value. Here we come in with the items minimum. And we drop off the other 50 here. So for efficiency's sake, think about how many times we have to ask a question. So, first model, we have that question that the computer has to calculate. At the top, it's got 1,000, right? 1,000 times it has to make that decision. At the bottom, because we now bring in 900, so altogether that computer has to make 900 comparisons, or 1,900 comparisons. 1,000 from the first people, we drop off 100, then it makes another 900. Each time we make a comparison, it takes a computer cycle, or 2, or 4, or 8. It takes some processing time. We compare it to this model. So now we have that same 1,000 at the top, but now we only have to make 500 decisions. So we went from 1,900 decisions to 1,500 decisions. That's a pretty big jump in terms of which way we want to do that. And you think, well, that's not going to take a computer long to do those extra 400. But let's imagine something a little bigger. Let's go to the IRS. Ooh, tax time. Everybody loves tax time. If I could speed up the processing of tax returns, but that same percentage, I would be a hero. So sometimes we want to think about, when we construct this, which way is going to be logically the most efficient. Now, when I design this for company XYZ, do I even have any clue though? I may not have a clue which way to go. Will both of them end up at the same logical result? Yes. So, and a lot of times you don't have any idea. But the general rule of thumb is we want to do the first question is the one that is least likely to be true. Least likely to be true. So some way we can rule out the most number of people the way we write those then is with an AND operator. So when we write them in our logical sense, we write them with something called that AND. And that AND means both halves of our comparison have to be true. Nearly every language allows us to write ANDs. And this is an AND comparison here. So the same thing. So if items sold greater than items minimum, and then we nest right inside of that an if statement of if value sold greater than or equal to value minimum, then bonus equals given. So in other words, we give them the bonus. So what we can do is we can write these together. To make it easier for us to write them, so we know what's going to happen internally. Internally, it's going to ask question 1, then question 2. So internally, the computer does this. Well, we're bright enough to know that we can break this down and we can rewrite it this way. And so we could say, if items sold greater than items minimum and the value sold greater than or equal to value minimum, then bonus. So we can shortcut that, and we can put a compound condition in directly. That makes our life a lot easier when we do this. But we have to remember, internally, this is what's going on. It makes that nested comparison. But if we can shortcut and write it this way, it makes life easier. All of these conditions, we tend to build something called a truth table. So a truth table says we have condition X and we have condition Y. So that X and the Y are our two questions. So X would be items greater than minimum. Y then is value greater than value of minimum. So we put these conditions together inside of a truth table. So if condition X and condition Y, we can evaluate them individually. We then can evaluate the entire expression based on that idea of a truth table. And so in that case, we know with an AND, both conditions have to be true. The only way that that entire expression evaluates true is if both sides are true. If I look at this, if any piece of this is false, that entire expression evaluates false. So ANDs, every piece has to be true to work its way through there. And so we have to be able to work with those processes because we know we're going to have questions that are going to be more than a simple, do you live in Peru? So we want to ask multiple questions and be able to do that. So, common things that we do. So, if I wrote this incorrectly, so if I rewrote this, and instead of nesting those if statements, I just put them in line with each other, and I said, all right, well, I know I have two questions, but I can ask them separately. So if items sold greater than minimum, yes, and they give a bonus, and then we evaluate items sold are greater than minimum, then we're going to give bonuses to people who didn't meet both criteria. And that's a pretty common thing people will do. They'll write something. In this case, we didn't put in a value. So notice that we didn't have this. So it's a lot of times it's really handy when I write those to put in that parenthesis and say, all right, let's explicitly write that out with parentheses, and we can see that items sold greater than minimum for bonus So parentheses are our friend. And so anytime we write these, so if I want to write an and condition, so I usually put parentheses in. So let's say I want to figure out if somebody can play women's basketball at Peru. So the first question we're going to ask, so is the student equal to female? What other item might we need to determine if you're eligible to play women's basketball at Peru? You have to be an active student. I was going to go grade greater than a 2.0. So now that we have those, we can evaluate a couple of those. So we know that if the student has checked male on a box, that they're not going to be eligible, right? And we know that if their grade's not over a 2.0, so let's say we get this condition. So, yep, they're female, and their grade is exactly a 2.0. So that's going to evaluate, that side's going to evaluate true. Their grade is exactly a 2.0. Is that going to evaluate true or false? That's going to actually evaluate false. So our entire expression's got to evaluate false then, right? So how could I fix that? Because I'm thinking, man, I think I rewrote that a little wrong. Is there a way to make that so if they have a 2.0, they can still play basketball? So this is a really common one we do. We think we want to say, so equal to or greater than 2. And so we think we want to do it at a 2.0. In that case, then, this is going to evaluate differently. So we're going to have a true. And that entire expression, then, is going to be true. So I actually did this not too long ago. I made a mistake writing out a formula inside of Excel. And we'll look at some of those in Excel on Thursday. I wrote it out and I said, okay, our normal grading scale is 90, 85, 80, 75, 70. So we have a grading scale like this, right? And when I wrote that, I very quickly put together a set of if-then statements so it could output a grade. Because I wanted it to put in, if you had a 90, that it would put in an A. So this would be your B plus, and so on. But when I wrote the whole set of those really quickly, I didn't put in the greater than or equal to, I just put in a greater than. And so if you would have scored exactly a 90, you would have gotten a B plus. Or if you got exactly an 85, you would have got a B instead of a B plus. So that's a really common issue we have when you write those, is to make sure that you get the correct expressions in there. So what happens, or what's a great way to do that, is to kind of work through. Kind of like we did here, where you start doing some test cases and go, oh yeah, that makes sense. So ands are pretty easy to wrap our heads around because we know that everything has to be true. So even if I wrote something very complicated, maybe we wrote a new rule and that has to be less than 25 years old. What other things could we put in there? And because we're giving away some weird new scholarship, and student equal Nebraska resident. So we did that with, in this case, there's 4 different pieces in there. But we know with an and that every single individual one of those has to be true, correct? So any of those would trigger that to say that entire expression is false. And if we wrote that out in pseudocode, that's really nothing more than 4 nested statements together. And so we could evaluate that. And we have ones where we get that complicated. So think about when you're enrolling for classes and trying to find a class. You want to find classes that are between 8:30 and 2 o'clock, and on Tuesday, and upper division. And so now you're making decisions, and only those classes that all of those criteria are true show up. Well, no, I don't really need to save that. So, ands are pretty easy to wrap our heads around. Now, we're going to introduce you to the ors. So, and ors, 2 different ways to do things. And says everything has to be true. An or statement says one of the conditions must be true. One or more, I guess we really should say. So in this case, we rewrote it. And so in this case, the salesmen have a little different criteria. Because we realize that, maybe we don't need to base it on just the value of the items. Because maybe we have somebody who sold a whole lot of items, but the value didn't add up, but they're very productive. Or we had somebody who sold only 1 item, but it was a brand new tractor for $300,000. So we should probably give them a bonus, right? So we're going to rewrite this to say or. So or statements end. So we want to give them a bonus if they meet either the condition of enough items sold or enough value sold. So in this case, when we look at what we wrote in the pseudocode, so if items sold greater than items minimum, then we give the bonus. Else, if the value sold is greater than the value minimum, then we give them the bonus. So what we really wrote is this. So we said, all right, so if items sold are greater than minimum, yes, they get a bonus. If that condition's not true, we pass it down to where they say, look at the number of value or the items in value, and they can also get a bonus. So, in OR questions for efficiency, it's opposite of AND. So in AND questions, we wanted to write the question we think is going to eliminate the most people first. In OR statements, we want to ask the question that is most likely to be true. So ORs, we want to have the one that's most likely to be true, AND's the one that's most least likely to be true. So what that does is, if we look at that efficiency again, that eliminates, so now we're looking at the same number of people going in. So we want to eliminate as many people as possible again. So in this particular case, items sold. So we have 1,000 people going in. Well, in this case, 700 people get a bonus going in. Great. 700 come out of here. 300 of them then enter the second question. And 180 of them don't get a bonus, 120 do. But that means we ask 1,000 plus 300. So we asked that question 1,300 times. We made the computer make a comparison 1,300 times. We compare it this way. So same 1,000 up here. But now we have 600 people entering this. So we have 1,300 versus 1,600 calculations or comparisons just by changing the order that we ask them. So, just like the ands, we can put these together in multiple OR. So we can write a truth table then for ORs. Truth tables, though, for ORs look a little different. So in the ands, any false condition made the entire expression false. In an OR statement, the only way that it's false is if all conditions are false, or you could think about it as it's true as long as there is a true condition somewhere. Either way you want to look at it. So, if both sides are true, the ORs are true. The whole expression is true. If we have a true-false, the expression is true. If we have a false-true, it's true. But if we have a false and a false, then the entire expression evaluates to false. So those are our two basic operators we're going to use. And there are some others. But the reality is most of the time we can use an and an or, and we can work around almost any kind of question we want to have. So we can do the same thing. We can combine them to make our life easier as long as you understand the logic behind it and how that's going to work. So internally, we know that that computer has to ask both sides of that question, but we can combine it for ourselves to make life a lot easier. So here we have the same question. If items sold greater than items minimum, or value sold greater than value minimum. And so we can put those together in a really nice package. So we can combine those just like we do in the and. So this week we have a couple of things to do. You have a quiz again. Most of you have done really, really well on the quizzes. And there is an assignment. And that assignment in the back of the book, we'll take a quick peek at a couple of them on Thursday. So make sure you have read the book on Thursday. We'll finish up the rest of the chapter, and we'll take a look at a little bit of the homework and how that works. So I will post a couple of those sample solutions so you can look at them. Be sure you look at them. And say, hey, okay, I see what I did. I can flowchart how do I sell products. And it gets easier in some ways because now once we combine that language so we can put multiple statements together. So we'll look at how we can do far more complex logic. And we'll look at those truth tables, and we'll introduce you also to what we can do with our friend Excel. Because before we get to anything else, we know that Excel can do a lot of these. And we can actually test out some of these conditions in Excel. All right, any questions on the homework? Any questions at all? Going once? Going twice?